All right, guys, so we just talked about equilibrium, where we have these two opposing processes, our reactants forming our products, and our products turning into our reactants at equal rates. So that is when we have our equilibrium. So this question now is, what happens if I change something when the system's already in equilibrium? Okay, so the scientist LeChatlier, French scientist, he was the one that kind of came up with this overarching principle of what happens if you disturb a system at equilibrium. Okay, so here's an example in our grocery store of the equilibrium of our shelves being stocked being disturbed, right? We have a snowstorm just like we had this weekend, and things are pulled off the shelves and the shelves are empty. So we can kind of have the same idea where we have we can change something about a system. So we can change the pressure, the temperature, or then actually change how much of one of our reactants or products we have. And what the system does is it fixes it. Okay, it's going to move or shift either toward the products to make more products to fix that, or move toward the reactants to make more reactants in order to make up for whatever change was occurring. So it's the idea of restoring balance. So I love to think about LeChatlier's principle in terms of a seesaw. So we have our reactants on one side and our products on the other. The goal is to stay level and balanced. Okay, and we're going to kind of refer to these possible changes as tipping our seesaw. So we might have a situation where now, let's make it look unbalanced. So now we might have a situation where we have our seesaw and we have way more reactants, right? Those are way heavier, pushing the seesaw down than products, and we'll have to adjust that to get it back to our level equilibrium state. Okay, all things in the world want to be in equilibrium, and so if a system gets disturbed when it's in this state, okay, it's going to try to fix it, which is what we call LeChatlier's principle. Okay, so again, we can kind of look at this as a seesaw, which we see up here, our reactants on the left and our products on the right, just how we would write a chemical reaction. Okay, so if a reaction needs to add more reactants to counteract the change, okay, so our change would mean for our first bullet point that we now have our products are way heavier. Okay, we have more products, they're pushing that seesaw down. So in order to change that, we have to add more reactants to kind of balance it back out. Okay, and I even will do this and stick my arms out left and right and kind of physically do it, which I think can help. So you can kind of try that as you're watching here. But if we need to add more reactants, we say that we are shifting left. Our reverse reaction is going to be more prominent, and so the direction of our reaction is left, the way we write it. Okay. The second bullet point says if we need to add more products. So what that would mean is our reactants are dominating right now. We need to get more products to even it back out. We need to pull that back down. When that needs to happen, we say our equilibrium will shift to the right, or our reaction will shift toward the forward reaction or toward the right. Okay, so that's kind of a setup in terms of how we can actually look at specific changes and specific reactions. This is kind of the more general idea. Okay, so we have a couple different things that could happen in order for a reaction to need to shift back to equilibrium. So this would be if we change the concentration or we change the amount of products or reactants that we have. So this is actually really a change in amount, okay, of products or reactants. So if we increase the reactant concentration, okay, if we increase the reactant concentration, now all of a sudden our reactants are heavier than our products. We have more of them. Okay, we have to shift that product side back down, so we're going to shift to the right. Okay, we're going to push the right side of the seesaw down in order to make our reaction back to normal. Okay, we can also think about this KEQ, go back and connect our equilibrium constant. If all of a sudden our reactants get way bigger, in order to even that back out and keep this constant the same, okay, we also have to increase our product concentration to make sure that that will stay constant. Okay, and then we can also see the opposite being true. So I'll do the opposite in blue. That's this one right here. Okay, so if our reactant concentration decreases, Okay, so now all of a sudden we have less reactants than we did before. That means our products are weighing us down. We have to fix that by making some more reactants. The reaction has to go in a direction in order to make more reactants. Okay, so that's going to be a shift to the left or toward the reactants side. Okay, we can also think about a change in temperature. Okay, temperature. So remember when we talked about exothermic and endothermic. Exothermic, okay, that means heat is a product. Okay, it's produced, right? Heat is exiting the system. When we have an endothermic reaction, okay, that means our heat is a reactant. So we're just going to treat heat as a product or reactant. That's it. So heat is a reactant. Okay, so if we think about this, okay, if we increase the temperature, we need the heat to go back down. We need to take some heat away. Okay, so we're going to shift toward the side without the heat. So if we're looking at this exothermic process that we have on the top, reactants to products, okay, and heat is a product in an exothermic reaction. If we added extra heat, that would be like adding extra product, and now all of a sudden our products are weighing us down. In order to relieve that change and relieve that stress that was put on the system is now going to have to work to make more reactants to alleviate and get rid of some of that heat, okay, in order to pull the reactants down to be more level. Okay. If the temperature decreases, that means we have to add more heat. Okay. All of a sudden our product concentration or the amount of products we have is lower than our reactants. We have to fix that by adding some more products, so we're going to shift toward the right. So the idea is we're really got to think about heat as a product or as a reactant, and we treat this then the same way as we did the previous slide where we had just changing the amount of products or the amount of reactants. All right. Our last change would be for systems when we have gases, okay, when either any of the products or the reactants are gases. Okay, and if we change the pressure, remember gases act kind of funny. So when we change the pressure or the volume, okay, we have to that's going to stress our system because our gases are hitting the walls of the container, and that's going to affect how our reaction functions. So if we increase the pressure, okay, we have to shift to make sure the pressure goes back down. So we're going to shift to the side with the least moles of gas. Okay, and remember our coefficients in front of something tells us how many moles of gas we have. So if we had 2O2 listed, that would mean we have 2 moles of gas. So if we increase the pressure, we have to alleviate that by making less gas. Okay, I don't want that pressure to be as high, so the system's going to shift in a direction that will allow the gas to be less confined in that container. Where the opposite is true, if we decrease the pressure, okay, then the gas has more room to spread out, and so we're going to we want that pressure to equal out, and we shift to the side with more gas, so now we can re-increase the pressure and make it at the place that it would like to be in the system. Okay, and we're going to show some examples of all three of these in a minute. Okay, so we're going to start with this reaction here. So we have hydrogen gas plus iodine solid, okay, makes hydrogen iodide, okay, or hydroiodic acid, if you would like. So what we see here is if the pressure is decreased, okay, so I'm looking at the pressure, what will happen to the equilibrium? Okay, so the pressure went down. So our goal is to equalize that pressure by making it go back up. Okay, if we decrease the pressure, we have to make it go back up. So we need to shift to the side with the most moles of gas. I need more gas to make the pressure go back up. Okay, so if we look at the left, we have 1 mole of gas, right? We have the 1H2 right there. Whereas if we look at the right, okay, that has 2 moles of HI, hydrogen iodide. So we're going to see 2 moles on the right. So if we want to increase the pressure, okay, to kind of counteract the stress that was originally put on, we need to shift to the right, to the side with the most moles of gas. All right. Next example, we have the same reaction, okay, and this time we're talking about temperature. So the first thing I'm going to do is I'm going to look and see, is this an endothermic or an exothermic reaction? We just have delta H listed. Remember, if delta H is positive, okay, that means it is endothermic. And I'm struggling with my spelling here. All right, endothermic. So that means our heat is a product, or excuse me, a reactant. So I'm going to go ahead and list that in. I'm going to rewrite the reaction, okay, and I'm going to list that in as a reactant. So if I draw my teeter-totter, okay, I'm going to draw the fulcrum there, and it says that the temperature is increased. So that is equivalent to adding more reactants. I added heat to increase the temperature, so I have extra reactants right now. Right, I added this heat, so I have extra reactants. So that means my reactants are heavier. In order to alleviate that change, I have to make more products. I have to use up that heat that was added in making more products. So that means our equilibrium is going to shift to the right. Okay, it's going to shift to the side in order to alleviate that stress. Push this lever back to being equal, to being level. And it does that by creating more products or using up the heat that was added. So again, the answer here is shifting toward the right. Okay. So I believe that might be the one we just did, right? So we're just going to go more. Okay. So now I'm adding more I2. Okay, I add more I2. When I add more I2, I'm adding more reactants. So again, my reactants are heavier than my products, so I have extra reactants. Okay, in order to alleviate that change, I have to use up that I2, okay, or make more products. Again, if we think about our KEQ, all of a sudden we've adjusted this so that our reactants are bigger than the products. I need to get that back to being a constant. In order to do that, then I have to increase the product concentration. Okay, when I increase the product concentration, that's going to be a shift to the right. So the system is going to fix the change of adding more I2, more iodine, by using it up. Okay, it's going to use it up in that forward reaction. And in using it up, we produce more products. Or we can think about that we just need to get more products. In order to get more products, we have to move in the forward direction or move toward the right of our reaction. Okay, on your homework, you're going to look at one reaction at a time and kind of look at these different stresses that would occur and see what direction the system would shift in order to alleviate the stress or alleviate the change that was put on it. All right, that is it for our new material, guys. So we have a couple more days when we get back to finish this up, review for the final. If you have any questions, we'll go over it in class whenever we are back in school.